Hello there and welcome back. We are to section 2.7 in Calculus 1, and we're going to be talking about derivatives and rates of change. And the easiest way to explain this is we have some generic curve f of x. And what's happening is we have a generic point, x is x and y is f of x. And we have a specific point, a. And what we want to do is we want to find, you see this line here? We want this difference to become zero, basically, to be as tiny as possible. So this distance here is we're going to be heading this way. We're going to shove x that way until we get as close as we can so that that difference is basically zero. Now, that creates a problem because we have the slope of that is going to be what we're looking at. And the slope of this line is right here. Remember y sub 1 minus, or y sub 2 minus y sub 1 over x sub 2 minus x sub 1. That's basically what we have here from your algebra class. So again, ideally, we're jamming this as small as we possibly can. And this curve over here really demonstrates that well. And we can see with this point here, this slope here, it looks like it's zero. And this is going to be our x sub 1, and then we have an x sub 2 here, x sub 3. And you'll notice we are progressively shoving x, and our goal is to get to a. And so we're shoving this x value that way. Ultimately, our goal is we want to know the slope of this red line right here. And I'm going to re-emphasize it with more red. This is the tangent line. These lines, let me write that, tangent line. These lines are called secant lines. And they give a decent approximation for what it is that we're trying to do. But what we're looking for is that tangent line. So for the rest of this lesson, that's what we're going to be focusing on. So let us focus on that. The tangent line to the curve y equals f of x at point A, comma f of a, is a line through P with a slope. And once again, we're trying to jam this as close as we can. We're trying to make that zero the best that we can. So we're going to end up with this. The slope is the limit as x is approaching a, that's what we're doing up here, x is approaching a, of f of x minus f of a over x minus a. And let's talk about that formula with our example here. Find the equation of the tangent line to the parabola y equals x squared at the point 1, 1. Now, I want to point out this is my a, the 1 there. And when I plug in a into here, 1 squared is 1. That's where that 1 comes from. Now we're going to compare this to point, or generic point, I should say, x, f of x, which in this case is x squared. So the slope of the tangent line is the limit as x is approaching 1 of x squared, so that's the f of x, x squared, minus f of a, which is the 1 there, over x minus a in this case is 1. Now you'll notice we have a problem. If I just plug in 1 here, I get 0 in the denominator, and that's never okay. So what we're going to do is we're going to play with it a little bit. And very nicely, this one factors. It's a difference of squares. And you'll note those go away. And so we get, when I plug in, this is as x is approaching 1. When I plug 1 into there, I get 1 plus 1, which is 2. So this is the slope of the tangent line. Now we're not done. We still need to build the equation of the line. So we're here, and remember, x naught, y naught is the 1, 1. So y minus 1 equals m, which we now know is 2 in this case. And I'm going to go ahead and put that into slope-intercept form. I'm going to distribute the 2. And here is the equation of the tangent line in slope-intercept form. Now, some teachers let you leave it like this in a point-slope form. Most teachers usually want you to go to slope-intercept form, so you'll have to ask your teacher, your specific teacher, if they care or if they have a preference. Okay, so now we are to a more useful way of viewing our same problem. So this is the exact same problem that we had here. Except now what we're saying is that difference between a and a generic x value is we're going to take a step size of h. And we're going to notice that this point right here is a plus h. And the y value is f of a plus h. And this point is a f of a. And what that's going to do is that's going to give us an alternate version. So our slope is going to be the y value, so f of a plus h minus f of a over, and this distance here is h. So that's our slope. However, that's our non-instantaneous slope, or I mean our, we're not calling it that yet. This slope of the tangent line. This is the slope of the secant line. The slope of the tangent line is going to be the limit as h approaches 0. So we want that gap, again, to go to 0. And you might recognize this. It's called the difference quotient. So back up to our definitions. These are saying the same thing. And we're going to be using this definition for quite a few things for the rest of this chapter. All right, let us move on. All right, and we're going to talk about velocities. Velocity is not necessarily the same thing as speed. Velocity, when you go into higher math, there's a more specific definition with when it's in vector form and so on. All right, so in general, suppose an object moves along a straight line according to the equation of motion, where s is the displacement and the object at any given time t. So I'm going to give a small lesson. And just to be clear, the average velocity is going to be the f of a plus h minus f of a over h. And of course, the instantaneous velocity at time a is going to be the limit as h approaches 0 of f of a plus h. And I'm going to give a small physics lesson, a little bit of a history lesson. Sir Isaac Newton, if you've heard of him, he's credited with creating calculus, although there was another mathematician that also created it at the same time by the name of Leibniz, actually even better than Newton did. But Newton created calculus because he had a physics problem that he needed to resolve, having to do with momentum and force and things like that. One of the formulas that he came up with, the height is going to be 1/2 the acceleration times t squared plus v naught times t plus h naught. Now, v naught is the initial speed or velocity. A is the acceleration. For our purposes, our a is going to be a negative 9.8 meters per second squared. Now, this is the universal on Earth acceleration of gravity when something lets go because of the gravitational field of the Earth, this is how quickly it accelerates. We're not including air resistance and things like that. So when I plug that into here, half of that is going to be a negative 4.9. So this is our formula that we're going to be using for something falling. And that is exactly what we are going to use for this one, because we have a ball that is going to be dropped from an upper observation deck of a tower that is 450 meters above the ground. Now, this number is different when we're talking about feet per second squared, obviously, and we have a good handle on what that is as well. And of course, this is an approximation. I do want to mention it's negative 9.8 because it's falling downward, and our orientation on Earth is upward is positive. So it's apropos to have it here. So they want to know the velocity of the ball after 5 seconds. So what we're going to have to do is we're going to have to do the difference quotient to find this. So h of t is negative 4.9 t squared. Now, in this case, v naught, down here, v naught is 0 because the ball is dropped. So when you let go of something, initially, it has no speed. So the v naught here is 0. However, the initial height is 450 meters off the ground. So this is our formula. Now, our velocity formula is going to be here. So v of t, actually v of 5, pardon me. It's going to be the limit as h approaches 0 of negative 4.9 times 5 plus h squared plus 450 minus negative 4.9 times 5 squared plus 450 all over h. Now, some interesting things are going to happen. First off, I'm going to notice that that minus minus becomes plus. Also notice that becomes minus 450. So you can see the minus 450 is gone with the 450. All right, I'm going to go ahead and FOIL that out. For h. And what I'm going to do is I'm going to notice negative 4.9 times 25 plus 4.9 times 25. Those are gone. So gone. And here I'm going to get negative 49 h minus 4.9 squared. So I guess plus 4.9 squared. H squared, sorry. And that is all over h. And very nicely, h factors out. Negative 449 minus 4.9 h. And notice those h's go away. Yay. And as h goes to 0, we end up with negative 49 meters per second. That's how fast. Now, again, it's negative because it's falling downward. So it's appropriate that the velocity is negative in this case. Now, that was part A. Part B. How fast is the ball traveling when it hits the ground? Well, we are going to do this again, but it's going to be when the height is equal to 0. And oh, I'm told not to do that part. Sorry. So we're going to move on. But if you did want to do it, it's when h is 0, the height is 0. You'd get that time, and then you would plug it into the formula again. Anyway. All right. Last page. The derivative of a function. So this is a more generic way of doing it. We talked about velocity and so on, but the way we write this is f prime of a, is how we say that, f prime, is going to be the limit as h approaches 0 of f of a plus h minus f of a over h. So we're going to find the derivative at the number a. So we're going to keep it a generic a. And so here we go. F prime of a is going to be, I'm going to replace each of these x's with an a plus h. Limit, as h goes to 0, of a plus h squared minus 8 times a plus h plus 9 minus a squared minus 8a plus 9 all over h. Okay, I'm going to FOIL here, I'm going to distribute here, and I'm going to distribute here. It's going to be a squared plus 2ah plus h squared. It's going to be a tight fit. Minus 8a minus 8h plus 9 minus a squared plus 8a minus 9. Ooh. All over h. And we're going to see here that we have an a squared minus a squared. We have a negative 8a and a positive 8a. And we have a 9 minus a 9. And we end up with 2ah plus h squared minus 8h all over h. And once again, you can see we can factor an h out. These are gone. And as h goes to 0, we end up with 2a minus 8. So if we did want to know the derivative at a specific number, we would just need to pop that number for a there. No, 2 times that number minus 8 is what we would get. All right. Example 5. Now we're going to use this information here. And they say, and you'll notice, just to be clear, that this function here is this function here. So they want to know the equation of the tangent line when x equals 3. You can see this is when x equals 3. So I'm going to pop 3 into there. So the slope of the tangent line is going to be 2 times 3 minus 8, which is negative 2. So now I'm going to do y minus negative 6 for point slope form equals negative 2 times x minus 3. And you can see y is going to equal negative 2x. There is the equation of the tangent line. So example 4 and example 5 complement one another. And the rates of change. So this is just, again, a different way of viewing this. We have our delta x, that's our change in x, that's h. H is delta x, those are the same thing. Delta y, so we're doing this in terms of increments. As x is progressing from one x value to the next x value. So delta x is defined as x sub 2 minus x sub 1. Delta y is f of x sub 2 minus f of x sub 1. And so delta y over delta x, which is here is referred to as, and this here, so if we do the limit as delta x is approaching 0 of delta y over delta x, and this becomes dy over dx, which we'll talk more about in another video. This is referred to as the instantaneous rate of change. And this is going to continue to be a bigger deal as we move through this. I hope you found that helpful.